All right, guys, here's our to-do list for today. What we're going to do is we're going to take these orbital filling diagrams that apparently you guys are really good at doing because you didn't come in and ask questions, and you didn't have questions as we were grading them, and your scores were relatively solid. So guys, you are screaming at me as a group, we're really good at orbital filling diagrams. Because understand, anytime you're talking to a group, there are always outliers. And guys, if you're one of those outliers, you've got to get engaged enough in this process to come and get help, because I can't help you if I don't know that you need it. So, guys, here's what we're going to do today. We're going to start today by drawing 3 more orbital filling diagrams. But guys, what we're going to do is we're going to use those orbital filling diagrams as the foundation upon which we're going to build these 3 ideas. So first of all, we're going to talk about how to change these orbital filling diagrams to make them represent ions. You may remember there are cations and there are anions, and when we filled in that table, when we did protons, neutrons, and electrons, you learned about ions. Well, guys, we're going to go back and revisit that and bring it forward to today. Then, guys, this is where the arrows go away. We are going to learn to draw what are called noble gas abbreviations. Now, guys, in order to do this, you need to know where the noble gases are in the... So grab your periodic tables and let's talk really quick. Do you guys, and maybe you know, you'd better know. You learned this, well, you didn't learn anything in 8th grade because you were so spun around you don't even remember it. Guys, where are the noble gases on the periodic table? Do any of you remember? They're on the far right-hand side. Guys, these are the noble gases right here. And what is true of all of those atoms? And the answer is they're completely full. Their S's and their P's and their D's and their F's are all completely full. And that's what makes them noble, because somebody that is noble is standoffish and doesn't want to interact with others. And that's the case for the noble gases. They are full, and therefore they don't react with other elements. We'll talk more in a minute. So you're going to learn to do noble gas abbreviations. Then, guys, you're going to learn to do Lewis dot structures, and that'll be our day. Get the idea? All right, here we go. So, guys, as advertised, we are going to start today by reviewing, and we are going to draw the orbital filling diagrams for these 4 atoms. So guys, what you're going to do in your notes is you're going to do these 4 right now. So you're going to do the orbital filling diagram for sodium, then chlorine, then copper, then arsenic. But guys, here's the deal. Leave 2 blank lines above and below each one of these and get them all on one horizontal line. Don't, like, arsenic's going to get a little long. It's element 33. Guys, try to not wrap this down to a second line. Try to get this all on one line. Now, guys, for those of you that were gone last time, unless you watched the screencast, you have absolutely no idea what we're doing. I'm not going to try to teach you. You missed about an hour and 10 minutes of material. I can't go back over that with you in 3 minutes. So guys, you're going to have to do your best to hang on. Maybe you learned the lesson that you should watch the screencast because this class is very progressive, and if you missed last time, you're sunk today. But guys, you're going to have an interesting weekend as you go back and rewatch the screencasts and try to catch up with what we're doing. You can do it, and once you've watched the screencast, I'd love to help you. But guys, you're going to have a little bit of, it's going to be an interesting day today. So guys, if you need help doing these, I'd love to help. I'll show you the answers progressively as you go. But guys, this is a great way to determine whether or not you're where you need to be. If you can't do these, you are not okay. And I'd love to help you if you'll invite me into the conversation. Trevor, are they coming back to you? Would it be helpful if we did the first one together? Just to sort of prime the pump a little bit? Happy to do it. So guys, I can even, I've actually typed up the answers, but I can show you what this one looks like. So guys, the logic goes like this. Sodium, element number 11, is in the 3s sublevel, but you can't start there. Electrons 1 and 2, these guys are in the 1s. So we write down 1s. Then guys, electrons 3 and 4 are in the 2s. So we write down 2s. Then electrons 5 through 10 are in the 2p. So we go like so. And then finally electron 11 is in the 3s. So we write down 3s. Then we need the boxes. The boxes represent the orbitals. We understand that the orbitals are actually spheres and dumbbells and clover leaves and all of those things. But we simply draw boxes. All of the s's have 1 box. All of the p's have 3 boxes. Then guys, we've got to put 11 electrons in these boxes. And so electron 1 goes there, electron 2 pairs up, spinning in the opposite direction. 3 goes there, 4 pairs up, spinning in the opposite direction. Now we get into a sublevel that's got more than 1 orbital. And guys, this is important. You got to remember that 5 goes there, but 6 does not pair up. 6 will go unpaired because there's additional space in the sublevel, and they want to go as unpaired as they possibly can. Now we've got to get numbers 8, 9, and 10. 8, 9, and 10 have to pair up. And then finally, guys, electron 11, which is the final electron in sodium. And this is the orbital filling diagram for sodium. And we can come back and check our work. And because sodium is 1 box into the 3s, we would expect it to have 1 electron in the 3s. And in fact, it does. Questions? Yeah. You know what? It actually doesn't matter, Kat. You could draw them up, down, up. That was down. You could draw them up, down, up, down, up, down, down, down. It doesn't matter. The only thing that you can't, what you're going to find is that I don't like to think if I don't have to. So I always go up first and then down second, but it doesn't have to be. The thing that does have to be is you can't go up, up. So when they're in a box, one will be up and one will be down. Whichever one you do first does not matter. Anything else? All right. So guys, let me just bring this in its typed out form. There is sodium. For those of you that are cruising along, are you ready to see chlorine, or am I going to give you the answer before you're ready for it? Can I throw you chlorine? Okay, so guys, chlorine then looks like this. Chlorine is at the end of the 3p. Notice that chlorine is 1 box short of the end of the 3p, and therefore it has 1 empty space in the 3p. Bless you. Then guys, we've got copper and we've got arsenic. I'll just give you copper right now because we actually did that one during class. I don't know if you remember, it was the second and last example we did during class. Copper is in the 3D and it goes like this. And then guys, I may as well just give them all to you. Here's arsenic. Now guys, here's the deal. If you don't know how to do these, I've obviously offered multiple opportunities to, hey, please ask questions. But guys, if you don't know how to do these, either because you were gone or because you still don't understand, copy these down. Because if you don't have these down, because guys, we're just going to fiddle with these for the rest of the day. And if you don't have these, whether you understand them or not, if you don't have these, you're going to miss out on the fiddling, and then you're going to be 2 experiences behind. So guys, if you're still not sure how to do these, in addition to watching the screencast and asking questions, guys, please write these down so that you can move forward with us today. So I'll give you a second to do that. The hope is that you can do them on your own. And then we're going to talk about ions, noble gas abbreviations, Lewis dot structures, and that'll be our day. Yeah?
Like I get probably
Great.
But I just don't really know like what everything means when I do it.
I know, right? Isn't that interesting? And you know what? I'll be honest with you. Did you hear what he said? He said, I know how to do this, but I don't really know what it means. It's like you've been trained 1S, 2S, 2P, drawing the arrows, but what does it really mean, right? Do the extra credit. Because if we tie this together, really what this means is, let's do this one. So the idea is this. The first, let me spit out my gum. So let's do like maybe sodium. So the first 2 electrons are in the 1s, but that looks like this. So those first 2 electrons are in a space that looks like this. Then the next 2 electrons are in the 2s. That is a bigger spherical space that looks like this. Then the next 6 electrons are in a 2p, and that's 1, 2, 3 dumbbell that look like that. Then the last electron is a 3s, which is this bigger sphere right here. So when you write down 1s, 2s, 2p, 3s, what you're really doing is this. You're saying a small 1s, a bigger 2s, 3 dumbbell-shaped P's, and then a larger 3s. So what you're actually doing is populating, if you will, the clouds from 1s to 2s to 2p to 3s, but we're doing it in a simplified way so that we don't have to get mucked up in drawing all those shapes. But that's what these boxes represent, is a small sphere, a bigger sphere, bigger dumbbells, and then an even bigger sphere. Yeah?
The reason why it's those shapes is because it holds that element?
Yeah, well, sort of. So why do the electrons go little sphere, bigger sphere, 3 dumbbells, bigger sphere, and then on from there? Why do they do this in the first place? And the answer is because if you're an electron, you have 2 forces that are acting upon you. You're trying to get, this is the nucleus, you're trying to get as close to the nucleus as you possibly can, right? There's attraction. But you're trying to get as far away from all the other electrons as you possibly can because there's repulsion. So how can you pack electrons into an atom so that they're as close to the nucleus and yet as far away from each other as they possibly can get? And the answer is put the first 2 in a little sphere. Put the next 2 in a bigger sphere. Put the next 6 in figure 8 shapes. Put the next 2 in an even bigger sphere. That's why they do this, is because they're trying to get as close to the nucleus as they can and yet as far away from each other as they can, and that's the easiest way to do it.
Like in the figure 8, like over here when the electrons are right there in the circle, and then it'll hit this electron over here in the circle.
Yes, and exactly. And so as they're pushing on each other, as this one, it's crazy, as this one moves, it makes all the other ones move, but as all the other ones are moving, it's making this one move, and they're all pushing on each other. And not just avoid each other, but still get close to the nucleus. Exactly, yes. Good. That's you exactly. But if you can, when you're doing this, as you said, I can do the mechanics, but I don't understand what it really represents. If you can picture in your head small sphere, bigger sphere, dumbbells, bigger sphere, then you have a sense of not just how they organize, but what their shapes look like. And that's the connection. Yeah, which is really the beauty of the extra credit assignment, which may be telling me instead of making this extra credit, we should require it. But not this year. All right. So, guys, are you all caught up with me? You ready to go? All right. So, guys, what you have now done is you have represented these 4 elements. And, guys, these elements are going to become our points of focus as you learn 3 things. First of all, how do we turn these into ions? Second of all, how do we make the representations easier by getting rid of the arrows? And then third of all, how do we make the representations even easier by only representing the electrons we really care about? And guys, guess which electrons we really care about? The ones on the outside, the last ones. All right, so you ready? Ions first. This is where you want to start taking notes. Skip down probably 3 or 4 lines so that your diagrams have space. Guys, here we go. Representing ions. Oh, I was going to ask these. Well, let's see. Do you guys remember what ions are? What are they? Good. They are atoms with a charge. Guys, remember you learned this, that the second day of filling in the proton, neutron, and electron grid? So guys, ions are atoms with a charge. How do we give atoms a charge? What do we mess around with? The numbers of electrons. Why not protons? Changes the identity of the element. Absolutely. So guys, how about this? Do you remember? We know the 2 types of ions are positive and negative. Do you remember the names? Do you really? Bingo. Cations and anions. Yep. So guys, remember not cations, it's cations. Do you remember, is a cation positive or negative? Positive, yeah, because the T looks like a plus sign. Guys, these are positively charged. And how do we form positively charged ions? What do we do with electrons? We take them weird, right? Positive means subtract them. But remember, because electrons are negative, we realized that made sense. So we make these by removing electrons. Perhaps you don't even need to write this down if you already knew it. So guys, if cations are positive, anions, of course, are negative, and these are formed by adding electrons. So guys, let me take you back to the kinder, gentler days of chemistry. You ready? Remember this stuff? When we used to draw circles, don't write this down. We used to draw circles to represent atoms, and what's in the middle? The nucleus, and what's in the nucleus? Protons and neutrons. And if this is chlorine, chlorine's got 17 protons because that's chlorine, and then the number of neutrons we find by subtracting the mass minus the atomic number. Then guys, chlorine's got 17 electrons, and that was chlorine. Remember that? Okay, so if you remember that, what about this? If we want to make chlorine negative, what are we going to do? We're going to add an electron. So now this is chlorine with a -1 charge, and we would write it like that. Remember that? Okay, so now what if we want to make it positive? Well, if we want to make it positive, we make this 16, and now that's chlorine -1. Remember that? What did I say? Did I say, oh, +1? I wrote it but didn't say it right. You remember that stuff? Now guys, here's the trick. Way back then, you learned that in order to give an atom a charge, you are either adding or removing electrons, right? But here's the problem. Which ones? Because guys, now what we know is that these 17 electrons are not jumbled in a pile around the nucleus. We now know that 2 of them are in the 1s, 2 are in the 2s, 6 are in the 2p, 2 are in the 3s, and the remaining 5 are in the 3p. So if we're going to start adding and removing electrons, which ones are we going to take away, and where are we going to put the electrons that we're trying to add? See the problem? We can't just say add or remove. We've got to talk about which ones. Well, guys, here's the answer to which ones. You want to write this down. Guys, the electrons that we add and remove are what are called the valence electrons. These are the electrons in the highest s and or p orbitals. So guys, the bottom line is this. When we remove electrons, we only remove the highest s and or p electrons. When we add electrons to make these things negative, we only add electrons to the highest s and or P sublevel. And these highest S and or P sublevels are what are called the valence sublevels, and these are called valence electrons. Valence means on the outside. So there's the rules. I'll let you catch up, and then we're going to figure out what this means. Y'all caught up? You okay? You good? Okay, guys, go back here. Ready? We're going to do this with sodium first. My encouragement would be to do this in pencil, or maybe just watch and see if it makes sense. Because, guys, you don't want to get all crazy and screw up your diagram. So if you're going to do this in pencil, that's great. But don't make a mess. So, guys, we've got a sodium atom. Sodium goes 1s, 2s, 2p, and then 1 electron in the 3s. Now, guys, what happens if we want to make sodium -1? Are we going to add or remove an electron? Add an electron. Where does it go? The only place it can, which is right there in the 3s. Got it? Okay. Now, guys, what about this? What if we want to go sodium -2? We're going to put 1 electron in the 3s. Where does the other one go? Nowhere. Sodium can't go -2. The only negative charge that sodium, and you're going to see these questions in multiple choice on the test. Guys, the only charge that sodium can take on that is negative is -1, because it doesn't have a place to put a second electron. Good? Okay, so now, guys, what about this? What if we want to go sodium +1? Will we add or remove an electron? Remove, and we will remove this electron. Does that make sense? Okay. Now, guys, what about this? What if we want to go sodium +2? What are we going to do? Take away 2 electrons. So we're going to take away this electron, and then which one next? No, you can't. Guys, the answer is this. Valence electrons are the highest S and P electrons. And as soon as you establish a third energy level, the second energy level is no longer highest. So the only highest electron that sodium has is this one. And once that one is gone, you're done. Get it? So, guys, what are the charges that sodium can take on? Can it go +1? Yeah, we can remove an electron. Can it go +2? No, because we can only take away 1 but not 2. Can it go -1? Yeah, we can add 1 electron. Can it go -2? There's nowhere to put the electron. Go ahead.
So, like, with P, it works to try and take away. But if it's like on the, I don't know. Yeah,
Let's go down and look at chlorine.
like the third one.
Yeah, let's look at chlorine and let's see if it answers your question. Kat or go ahead. Let's get there, because you're going to find out I chose these 4 with very specific purposes, because they're going to bring up all the little subtle weirdness but I love that you're thinking ahead. So, guys, let's do this. Chlorine -1. Can we do it? Yeah, the electron goes right there, right? Can we do chlorine -2? No. We can put 1 electron right there, but there's nowhere to put the second. Get it? Okay. So now, guys, what about this? What if we want to go chlorine +1? Can we do that? Yeah. Now, guys, which one will we take away? And check this out. It's not this one. Yeah, because remember how we put them in. We go 1, 2, 3, then we pair up 4, 5. So they come out in the order opposite they went in. So, guys, if we're going to go chlorine +1, we're going to take that one. What if we go chlorine +2? We're going to take this one. Is that okay? Then, guys, chlorine +3, chlorine +4, chlorine +5. Can we go chlorine +6? Yes. Guys, it's the highest S or P. So we can go 6. Can we go chlorine +7? Yes. Can we go chlorine plus 8? No, because then we go down into the second energy level. Good? Okay, so now guys, let's look at this. Now we're looking at copper. Ready? Let's do copper minus 1. Where do we put the electron? Nowhere. You can't. Guys, it's the highest S or P. The only hole that we have is in a D, and that is not on the outside. The D is smaller than the S. So guys, copper cannot be negative. Copper has nowhere to put the electron. So now what about this? Copper plus 1. Can we do it? Which electron are we going to take off? This one. What about plus 2? This one. What about plus 3? Can't do it. Abby, did that answer your question? All right. So now, guys, let's look at arsenic. Can arsenic go minus 1? You bet. Where does the electron go? Left, middle, or right? Left. So we can go minus 1, and then we can go minus 2, then we can go minus 3, minus 4? No. Then, guys, what about the other direction? What if we go plus 1? Gone. Plus 2? Gone. Plus 3? Gone. Plus 4? Oh, yeah, but not the D's. Yeah. Plus 4? Yep. Plus 5? Uh-oh. Sorry. There we go. So, guys, we can go plus 5 right here. What about plus 6? Can't do it. You guys okay? You get the idea. Go ahead. Yeah. Are you talking about this P? Yeah. Okay, think about remember we were talking about what this looks like. So we've got 1s, which is a sphere. We've got the 2s, which is a sphere. We've got the 2 p's. That went way better than I thought it would. We've got the p's that look like this, and then we've got the 3s. And that one electron is in the 3s. That's the outside of the atom. And the only thing we can mess around with is the outside of the atom. We can add to the outside, we can remove the outside, but we can't mess around with this. So once we establish the 3s as the outside, all of this is off limits. Is that okay? Go ahead. Yes. Keep going. So let me do this. I don't know how no, I got to draw clover leaves. I can't even do. Okay. So none of those have it exactly right so that I can show it to you. But the idea is this. So we've got the 1s, the 2s, the 2 p's, the 3s, the 3 p's. That wasn't so bad. Then we've got you see where I'm at? I just did through there. Is that okay? So now we've got the 4s. And the 4s is out here. Now, here's the trick. The 3D, and they're all I'm going to just change colors hoping that it'll stand out. The 3Ds are these clover leaf shapes, and I'm not going to draw a ton of them. And then there's that weird one with the circle in the middle. But the trick is the 3Ds, and there should be 5 of these, are a little bit smaller than the 4s. And then we've got the 4p's that are actually as big as the 4s's. So the D's, these guys right here, are actually smaller than the 4s and the 4p. So the D's will never be on the outside. They're always a little bit inside. What's that? And we know that from the periodic table because it's always D minus 1. Remember, the number tells us the size. And before we get into the 3D, we always start the 4s. So the s's are always bigger than the d's. Does that make sense? Okay, you guys good? All right. So guys, now that you understand ions, you ready to make the arrows go away? Okay, so guys, here's the deal, and let's just be honest about this. By the time you were done doing the homework, or by the time you were even done doing this, you were sick of drawing arrows, right? So guys, let's talk about why these orbital filling diagrams are powerful and yet a horrible waste of time. So guys, what is it that makes these things tedious? Well, sir, the arrows, and that's valid. We're going to get rid of the arrows. But what else makes them tedious? It's always the same stinking thing. Guys, look, you want to know how I drew these on the computer? I actually drew arsenic, and then I deleted the P's and turned it into this. I deleted these and turned it into that, and then I deleted those and turned it into this. They're the same bloody stinking thing over and over and over, and it doesn't change until the end. But guys, why is it the same stinking thing over and over and over? And the answer is because we're always starting at the 1S. Guys, we're always starting here and then building out to where it actually gets a little interesting. So guess what we need? We need a new starting point. Guys, we are now going to give ourselves a new starting point. Listen close. Here's the idea. No longer do you have to start in the 1S anymore. You don't have to start at hydrogen anymore. Guys, what we are going to allow ourselves to do is start at any of these noble gases. Now guys, why do we choose the noble gases as acceptable starting points? They're full. And if we can say that this is a point of fullness, then we can just build on top of that and get into the stuff that changes. You get it? Okay, so guys, write this down in your notes and then let's do them. These are what are called, you can just write down NGAs. These are called noble gas abbreviations. So guys, what do noble gas abbreviations do? Again, you can just write down NGA if you want. Noble gas abbreviations, and guys, you know what? I take that back. Just write down noble gas or NGAs and don't take notes. Let me just show you how to do these. So guys, the deal is this. Noble gas abbreviations provide you all the same information that's contained in the orbital filling diagrams, but they get rid of the arrows. We are no longer going to draw boxes and arrows. But guys, what do the arrows represent? Electrons. So instead of drawing arrows to represent the electrons, we are going to count the number of electrons and make them a superscript. You'll see what I mean. Then guys, we are not going to start at hydrogen each time. Instead, we're going to go back to the nearest preceding noble gas. I'll show you what I mean in a minute. Go ahead. Well, hydrogen's not, but helium is. And so we could use helium as the basis for a noble gas abbreviation. Watch. You ready? Here we go. So guys, go back to this. Go back to your stuff that you got. And we are going to do the noble gas abbreviations for these. You ready? Check this out. You're going to like this. So guys, take a look at sodium with me. What is the noble gas that is closest to sodium without going past it? We're going to go back to neon. And where is neon? The end of which sublevel? 2p. So guys, here's what that means. This is the electron configuration of neon, right? Neon takes you through the end of the 2p. So we're not going to write the 1s, 2s, 2p anymore. Whoa. We're just going to write neon and then 3s. Guys, notice it's got to be in brackets. It cannot be parentheses. So we're going to go brackets neon. And now guys, watch. Now let's get rid of the arrows. How many electrons are in the 3s for sodium? 1. That guy right there. Count it and make it a superscript. That's it. That is how we're going to represent sodium. Neon, 3s1, you're done. Let's keep going. So guys, now we've got chlorine. If we're looking at chlorine, can we go to argon? No, we're not there yet. You got to go back to neon. So guys, all of this is neon. So we're going to go neon, and then in addition to that, we've got the 3s. How many electrons are in the 3s? 2. Then guys, we've got the 3p, but notice guys, in the 3p, it's not full. How many electrons are in the 3p? 5. So that would be neon, that would be chlorine. 3s2, 3p5. You good? Okay, let's do the rest of them. Guys, now we're on copper. Can we go to krypton? No, we go backwards to argon, and argon is at the end of the 3p. Is that okay? Then guys, we replace all of this with argon. Be sure to put that in brackets. It matters. Then guys, in addition to that, we've got the 4s with 2 and the 3d with 2, 4, 6, 8, 9. Good? All right, one more. Now guys, we're on arsenic. Arsenic also goes back to argon. So that takes us through here. And then guys, we've got argon, and we've got 4s, 2, 3d, 10, 4p, 1, 2, 3. Do you buy it? You good? All right. So now guys, it's time to have the conversation. You ready? Okay, here's what you need to do. Find sodium on your periodic table. Got it? Number 11. Now guys, super squint, like this. And then look right above the word sodium. Holy shnikes. These are all on your periodic table. Oh, baby. All of a sudden, your $2 investment seemed like a pretty good buy. Now, guys, here's the deal. If you look at sodium, it says neon 3s1. That's cool. Now, guys, go over and look at chlorine. Neon 3s2, 3p5. We good? All right. Now, guys, go down to copper. Argon 3d10, 4s1. Uh-oh. 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 Guys, we got problems. Let's talk about the problems. Guys, on the periodic table, they put the D before the S. Why? Because the S is actually on the outside. The periodic table puts them in order so that the valence electrons are last. We put them in order that they fill. So guys, if I put copper on the test, and if you were to write down argon 3d10 4s1, I'm going to mark it wrong. Because it's wrong given the way that we learned it, because we put them in the order they fill and not the valence electrons last. But guys, it gets even worse than that, because look at what we put for copper. We put 4s2, 3d1, or 3d9. They have 4s1, 3d10. What's going on? Well, it turns out in copper, one of the electrons jumps out of the S and into the D. I don't want you to know that. We talk about this in AP. We're not going to talk about it in here. So guys, here's the deal. These are on the periodic table. Use them as an aid, but if you use them as a crutch, you're going to fall down. Because I'm going to pick ones that don't follow the trends that the periodic table uses, and if you blindly copy these down, they're going to be wrong, and I know that makes me evil, and I don't care. You guys okay? All right. So now, guys, let's have the other conversation. You look at these and you go, man, oh man, these are easy. This is better, this is faster, this is cleaner, this is simpler. But guys, here's the problem. This is actually more work. Because you're going, okay, I know how to figure out neon 3s1. But guys, just a minute, Kat, how did we figure out neon 3s1? Well, we did the orbital filling diagram and then pared it down. And guys, if we've got to do the orbital filling diagrams before we do the noble gas abbreviations, this is more and not less work. You see what I'm saying? So the question is, how do we do the noble gas abbreviations without doing the orbital filling diagrams first? Let me show you. Kat, are you okay if I ignore you for a minute? Okay, so, guys, we are going to do these. Write these down in your notes. Let me show you how to do these without doing the orbital filling diagrams first. Okay, so find magnesium. It's element number 12. You got it right there? Okay, now guys, watch. Here's all you got to do. Go backwards till you hit a noble gas. Which one do we hit? Neon. Write it down. Bless you. All right, so now we got neon. Guys, that takes us through here. Now, to get from here to magnesium, which sublevel are we in? The 3s, but guys, watch. There are 1, 2 electrons in the 3s, so we go 3s, 2, boom. Do you like it now? Better than even before? Yeah. So guys, now let's do gallium. Gallium is element number 31. Which noble gas do we go back to? Argon. Good. We go argon. And then guys, in addition to argon, we've got electrons 19 and 20. Just a minute, Abby. We got a 19 and 20, which are where? 4s, 1, 2. So we're going to come over here and go 4s, 2. Then guys, we've got all 10, 2, 4, 6, 8, 10. We've got all 10 of these electrons, which are where? 3d. And there are, in fact, 10 of them. Then, guys, we've got this last electron for gallium. And where is this? 4p. And there is 1 electron. Go ahead, Abby. Why don't we go, in, like if we're doing gallium, why don't we go to krypton? Because there's no way to represent fewer electrons. We can say here and then more, but we can't say here and then less. There's no way to represent a lack of electrons. And when we look at gallium, gallium has fewer electrons than krypton, and there's no way to represent fewer, but we can represent more. Does that make sense? Okay. So guys, oh, look at the curveball I threw you on number 3. It's an ion. Here we go. Guys, iodine is number 53. Which noble gas do we go back to? All right, we're okay. We're going to go krypton. Then, guys, in addition to krypton, we've got the 5s with 2, the 4d with 10. Then, guys, in addition to that, for iodine, we've got 1, 2, 3, 4, 5 electrons in the 5p. So we've got 5p5. But if we want to give it a -1 charge, what do we do? 5p6. And that would be iodine with the -1 charge. Good? All right. Kat, just a second. Go. Right now? I'd be happy to. Not now, because we don't have to do that anymore. Now that we're doing noble gas abbreviations, we don't have to start here anymore. So 1s, 2s, 2p, then the 3s, the 3p, like that? I'd be happy, but it's on your periodic table if you follow them in order. I'd love to show you though. Don't forget that, but that's the beauty of these noble gas abbreviations. We don't have to go back there anymore. I'll sit down with you in just a minute. Go ahead.
So when you write, if you just write that noble gas abbreviation,
Yeah.
does that not imply that it's a different thing?
Oh my gosh, guys, did you hear that? That's super brilliant. Guys, check this out. If we understand that this is iodine -1, right? But if we didn't know that this was iodine -1 and we saw 5s2, 4d10, 5p6, we go 5s2, 4d10, 5p6, that's xenon. Guess what? It has the same electron structure as xenon. So iodine with a -1 charge has exactly the same electron structure as xenon. But is it xenon? No, because we didn't mess with the protons. But you hit on the very foundation of the next unit. Because what you're going to find out is that electrons gain and lose electrons when they bond to take on the electron structures of the noble gases. And that's exactly where this is headed. So is it xenon? No. Does it have the electron structure of xenon? Yes. And the name for that is isoelectronic. So iodine -1 and xenon are isoelectronic. They have the same electron structures. Yeah. You guys good? Okay, guys, let's do strontium +2. So strontium is, thank you. Strontium, guys, is element number 38. Here we go. So we're going to go krypton. And in addition to that, we've got krypton. We've got 5s2. But now we want to give it a +2 charge. So what do? Remove the 2 electrons. So guys, here are your options. You can erase it, and that's legit. Leave it there. You can put a 0. That is fine as well. What you can't do is this. Do not erase 5s. You can put 5s0. You can put 5s nothing, but don't erase the 5s. How are we doing on noble gas abbreviations? All right. Good. If you like those, you're going to like these better. Guys, do not take notes, just watch. Now we're going to make these even more focused. We're going to make these even more focused and useful. So guys, remind yourselves, what does valence mean? You learned it 10 minutes ago. What does valence mean? On the outside, which electrons are valence? Highest, S and P. Now guys, watch my hands. How many electrons can be in the S? 2. How many electrons can be in the P? 6, for a total of 8. And guys, that's where we're headed with this, is you're going to learn to draw elemental representations that only include the valence electrons. And there can only be 8. 2 in the S, 6 in the P, and these are called Lewis dot structures. So guys, please don't write this down, just watch. Lewis dot structures only represent the valence electrons, and we write these surrounding the abbreviation for the element. Now guys, let's make sure you're clear which electrons are valence, highest, S, and or P. So guys, these are the S's and the P's, right? Doesn't matter which energy level, 1s, 3p's. Now guys, remind yourselves, watch closely. How do we put the electrons in the S's and the P's? So we got the S, we've got the P's, and the first electron goes there. Where does the second one go? Paired up, spinning down. Third electron goes there. What about number 4? Unpaired. Number 5, unpaired, then paired, paired, paired. Remember? Now you're going to do the same thing. Don't do this, but watch. But what we're going to do is to turn this into a Lewis dot structure, we're going to write down the abbreviation of the element. There is not an element XX. This is just an example. Now guys, focus. Don't look away, guys. You're going to miss this. So it goes like this. We've got the S orbital and the 3p orbitals, right? We are going to represent the S as being a box above the abbreviation. Then the 3p's are going to wrap around the sides. Okay? But guys, we are not actually going to draw these boxes. Imagine that they are there. But now, inside these boxes, we are not going to draw arrows, we're going to draw dots. So watch. Getting rid of the boxes, but realizing that mentally they're still there. Which electron is that? First one in the S. Where does the second one go? Paired up. Then, guys, the next electrons, 3, 4, and 5, go unpaired in the P's, and then they come back and they pair up around the outside. You get it? No? Are you okay or no? Okay, let's do it again. Okay, here we go. So here's the idea. Are you okay with the idea that the first two pair up, and then 3, 4, 5 unpaired, then 6, 7, and 8 paired up? Is that okay? Okay, now we're following that same pattern, only now the S is up here and the P's are around the outside. Okay? And now we're going to get rid of them because we really don't draw them. But similarly, electron number 1 is there, that guy. Electron 2 pairs up. Then 3, 4, 5 unpaired. 3, 4, 5 unpaired. Then 6, 7, 8 paired up. 6, 7, 8 paired up. Good? Okay, go ahead, Abby. No, it's only, good question, are there levels to them? And the answer is it's only always the highest, because those are the valence. Is that okay? Okay, so guys, do this with me now. Go back to your notes and let's do sodium. So guys, here's what you do. Write down Na for sodium. Now, how many valence electrons does sodium have? It's in the 3s. Guys, it's only got 1. Draw a dot. That's it. That's the noble gas abbreviation for, or the Lewis dot structure for sodium. Guys, now let's do hiccuping. Let's do chlorine. So, are the 3 P's valence? Highest S and P. Yeah. Are the 3s valence? Yes. So how many valence electrons do we have? 1, 2, 3, 4, 5, 6, 7. So how do we do them? Electron 1 goes there. Yes, good, Jeremy. Electron 2 pairs up. Now, guys, what about 3, 4, and 5? 3, 4, 5 unpaired. Then, guys, 6 and 7 pair up. Good? Go ahead. No, the order doesn't matter, but what does matter is you're going to end up with 2 pairs and 1 unpaired. So guys, you ready for another aha moment? See this space right there? See this space right there? Plug them together and what do you get? Table salt. Let's keep going. Chemistry. All right. Now guys, copper. Are these valence? No, they are not in the highest S or P. Our only valence electrons for copper are in the 4s. 1, 2, done. Now, guys, let me let you in on a secret. The S electrons do not have to be on the top. You could put the S on the left and then the P's top, bottom, and right. It really doesn't matter. But one of them is the S, the others are the P's. So you actually could do copper like this if you wanted to, and it doesn't matter. They just have to be paired up. Okay? So now, guys, let's do arsenic. Arsenic has got valence electrons in the S and the P, so we go arsenic. What about these 2 electrons? Paired up. And let's not do them on top, just to do this a little different. Those are our S electrons. I just put them on the right. It doesn't matter. But they have to be paired up. Then, guys, our P electrons, we've got 3 of them, and they will go 1, 2, 3, and they will be unpaired. You good? All right. But now, guys, we've got another problem, don't we? We made more work rather than less, because all that we know how to do right now is draw Lewis dot structures if we've got the orbital filling diagrams first. So how do we do these without doing the orbital diagrams first? Guys, watch. Watch. How many valence electrons does sodium have? 1. Find it on the table. Now, guys, watch. How many valence electrons does chlorine have? 7. Find it on the table. How many valence electrons, skipping copper, does arsenic have? 5. Find it on the table. Do you see the connection? Guys, sodium has got 1 valence electron, and where is it? The first box. Chlorine has got 7, but it is in the 1, 2, 3, 4, 5, 6, 7th box. Arsenic has got how many? 5, but it is in the 1, 2, 3, 4, 5th box. And now you're going, wait a minute, what about the D's? Why did you skip them? Why did we skip them? They're not valence. So guys, then the question becomes, what do you do with something that's in the D sublevel, like copper? Well guys, how many valence electrons does copper have? 2. But look, copper's right here. It's got a pant load of D electrons, but those aren't valence, so the valence electrons are the S electrons you put first. So how many valence electrons do all of these have? 2. So guys, it goes like this. 1, 2, 2, 2, 3, 4, 5, 6, 7. Noble gases are full with 8. Get it? So let's do it. Let's do the examples, and then Kat, I'll do your question. So guys, here we go. Magnesium. Guys, here's the trick. Never, never, ever, never, ever on the test. So let's do this. So magnesium's got how many dots? 1, 2. Don't do this. Guys, never put your dots on my writing, my typing. Always rewrite it and then do your dots. You'll see why in a minute. So guys, the only way that you can screw up magnesium is if you do this. Why is that wrong? Yeah, they're the S electrons. They've got to be paired up. So now guys, let's do gallium. Gallium is right here. How many valence electrons? 1, 2, 3. What about the D's? They're not valence. So we go gallium. What do we know about the first 2 dots? Paired up. 1, 2. Doesn't matter where we put them. They just got to be paired. And then we've got 1 more electron. Where does it go? Doesn't matter. Let's do it over here. That's gallium. Okay, now guys, let's do iodine -1. Iodine has got 1, 2, 3, 4, 5, 6, 7. So we go 1, 2, 3, 4, 5, 6, 7. But it's with the -1 charge, so what do? Add 1 more, and that's 8. Now guys, here's the thing you got to realize. Never put charges in your Lewis dot structures. That's why I'm telling you not to draw your dots around my diagrams, because if you do and my diagram's got a charge in it, it's wrong. Never put charges in your Lewis dot structures. How are we doing? 2 more? 2 more? Okay, so selenium. Selenium is right here. 1, 2, 3, 4, 5, 6. So guys, selenium's got 6. And we go 1. Where does it go? Paired up. Then we go 3, 4, 5, and then 6 has to pair up. Now guys, selenium's got +1 charge. Which one goes away? Yeah, the one got placed last. They come out in the opposite the order opposite they went in. So guys, this one went last. So it comes out first. Does that make sense? A better way maybe to think about that is guys, the subtraction first. Selenium's got 1, 2, 3, 4, 5, 6. Do the subtraction first, and instead of 6, do 5, and then you'll do it right every time. See what I'm saying? Because then you'd go selenium, and you'd go 1, 2, 3, 4, 5, and that just works. Good? Okay, so now guys, calcium. Calcium's right here. It's got 1, 2 electrons. So we've got calcium, and we go 1, 2. But now let's give it a +2 charge. What do? Take them off. That's it. Now, guys, does this mean calcium has no valence electrons? No, actually what it means is calcium's got these 2 valence electrons in the s. When they come off, it exposes a full valence shell in the 3s and the 3p, and it actually has the electron structure of argon, making it stable. But we draw it like that. Kat, you had a question. How we doing, gang? Go ahead. Yep.
So, if it is in the D section,
Yes.
like why is?
Give it 2 dots. Everything in the D's always has 2 dots because to get into the D's, you'll go through an S first, and those S electrons are always the valence. Okay, guys, so check out your homework. Assignment number 4. Here's what it says. It says, write the noble gas and Lewis dot structures for the following atoms and ions. And guys, you'll notice that it's 2-sided. I did that on purpose because here's the thing you're going to do if you follow the directions. You're going to cripple yourself. Because guys, notice what it says. It says, draw the noble gas abbreviations, then the Lewis dot structures. And guys, if you follow those directions, you're going to find quickly that in order to do the Lewis dot structures, you're going to have to do the noble gas abbreviations first. Because you'll do the noble gas abbreviation and then you'll do the Lewis dot structure off of it. This would be my suggestion, totally up to you. On the front of this, I would do noble gas abbreviations first, Lewis dot second. Then on the back of this, I would do Lewis dot first, noble gas second, so that you can do one without the other in both directions. You know what I'm saying? So guys, when I see you on Tuesday, we will grade this homework assignment, and then it's go time for the test. Guys, we have posted a very detailed test review on our website. I would strongly encourage you to grab that just a second and dig into it as you study. If you're not sure how to do that, I'd love to chat with you. But guys, understand the last page of the test, and it says this on the study guide, the last page of the test is orbital filling diagrams, noble gas abbreviations, Lewis dot structures. You can't pass this test without knowing how to do those. Yeah. No, yeah. So guys, the noble gas abbreviation for a noble gas is not the noble gas. You've got to go back to the previous noble gas and build up from there. You'll notice it does that on the periodic table as well. For neon, it actually gives, well, for argon, it gives you neon 3s2, 3p6. You always go back to the previous noble gas. So guys, there you have it. I would love to be available to you if you need help. That is all